In this video, we explore the JAX framework with a specific focus on parallel computation and parallel programming. We'll learn how to run code across multiple cloud TPU chips, which are specialized hardware devices provided by Google. While you can access multi-TPU setups through platforms like Google Colab, we'll take a more advanced approach using Google Cloud directly, as this allows us to work with larger pods of the latest TPU chips. To begin our project, we need to set up our environment. First, we navigate to the Cloud TPUs page in Compute Engine in Google Cloud. From the TPUs page, we select Create TPU and choose our settings. For this demonstration, we'll use the US Central 1 region and configure an 8-chip TPU V5E setup. We choose Ubuntu as our operating system because it provides helpful additional utilities and makes the system easier to use. It's important to note that this is a paid hardware configuration and the costs can be substantial. After creating our virtual machine, or VM, we connect to it using SSH. Once connected, we install the JAX library using pip, making sure to include the optional TPU components in our installation. With our environment ready, we open a Python interpreter to start exploring JAX commands. Our tutorial will cover 3 different types of parallel computation. First, we'll look at automatic parallelism using the JAX just-in-time compiler. Then we'll explore semi-automated parallelism, which combines the compiler with sharding constraints. Finally, we'll examine fully manual parallelism using tools like sharded maps. Our first step is to check our available devices using JAX. When we do this, we can see that we have 8 TPU V5E devices at our disposal. For those following along in a notebook environment, it's important to note that the V5E TPU runtime will only provide a single TPU chip. If you want to explore multi-chip setups in a notebook environment, you'll need to use older TPU versions. Let's explore data sharding, which refers to how data is organized across available computing devices. The standard array object in JAX is specifically designed for distributed data and computation. Each array comes with an associated sharding object that describes how the data is distributed across your available devices. To understand this better, we can create an example array and examine how it's laid out on our hardware. Using the devices function, we can see that our initial array is located on the first TPU chip. The sharding information is relatively simple at this stage since we're only using a single device. To get a clearer picture of how our data is organized, we can use the debug library's visualize array sharding function. Before using this visualization tool, we need to make sure the rich library is installed on our virtual machine. Moving to more advanced concepts, we can implement explicit sharding. This process is more complex and requires us to use what's called named sharding. Named sharding specifies a grid of devices with named axes and requires a mesh configuration. We create a sharding specification and pass it to our device put function, which places our array across devices according to our specified configuration. When we visualize the setup, we can see that our array is now distributed across all 8 TPU devices. Once your data is sharded, the simplest approach to parallel computation is to pass the data to a just-in-time or JIT compiled function. One of JAX's powerful features is that you only need to specify how you want your code's input and output to be partitioned. The compiler handles everything else automatically, including managing communication between devices. To demonstrate this, we run an element-wise computation on a range of values. The computation for each shard is performed on the device that holds that particular shard of data. This follows a general principle in parallel computing. Computation typically follows the data's location. As computations become more complex, the compiler makes intelligent decisions about how to best distribute the data sharding. Let's explore a more complex example where we sum along the leading axis of our data array X. When we visualize how the result values are stored across multiple devices, we see an interesting pattern. The results are distributed across TPU pairs. TPUs 0 and 7 work together, as do TPUs 1 and 6, TPUs 2 and 5, and TPUs 3 and 4. This pairing occurs because we're performing a summation across the X dimension. This example demonstrates the powerful capabilities of JAX and TPUs for handling large-scale parallel computations. For situations where you need more control over how your data is distributed, JAX provides the with sharding constraint function. This function can be used together with the JIT just-in-time function to give you greater control over how the compiler distributes intermediate values and outputs. To illustrate this, let's revisit our previous fcontract function. Instead of having the output partially replicated, we can specify that we want it fully sharded across all 8 devices. While the numerical results remain the same, the visualization of the array sharding looks quite different because we've specified a new output sharding pattern. For the highest level of control over parallel operations, we can use manual parallelism with shard maps. This approach requires working with meshes and the shard map function. The shard map function is unique because you write code to handle just a single shard of data, and the function then constructs the complete parallel operation. When using shard map, you must provide 2 key arguments: inspec, which determines the shard sizes, and outspec, which specifies how the blocks should be reassembled. We demonstrate this using our previously created f-element-wise function. An important detail to understand is that the function we write only processes a single batch of data at a time, which you can verify by examining the device's local shape. This local perspective is crucial for understanding how your code interacts with the distributed data. Working with aggregation functions requires special consideration in this context because each function only sees its device's local portion of the data. For example, when we use a shard map with JAX's NumPy sum function, the function operates independently on each shard, and the summation only reflects the local results. If you need to sum across all shards, you must explicitly request this using collective operations like lax psum. This gives us the complete sum across all 8 shards, resulting in the number 496. Since this final result no longer has a sharded dimension, we set the outspecs parameter to an empty partition specification. This approach to parallel computation with JAX demonstrates a progression from simple to complex control over data distribution and processing. We started with basic automatic parallelism, where JAX's compiler handles most of the work for us. We then moved to semi-automated parallelism, where we could influence how data and computations are distributed using sharding constraints. Finally, we explored fully manual control using shard maps, which gives us precise control over how each piece of data is processed and how results are combined. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include a link to the documentation in the description as well. If you have any questions, please post them in the comment section, and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.